Unit 2, Elements and Molecules, Lecture 3. In this next section on nomenclature, we're going to organize it very thoroughly. We will talk about binary nomenclature, ternary nomenclature, quaternary nomenclature. We'll mention hydrates, and we'll talk about some common names. Let's start with binary nomenclature. Now, when we talk about binary nomenclature, there are three areas we must address. We must talk about the binary compounds that are composed of two nonmetals. Then we must talk about specifically binary acids, which are composed of a nonmetal and a hydrogen. And we talk about the binary compounds that are composed of a metal and a nonmetal. So we'll have three different areas, and you will recognize them because binary compounds are compounds of two different elements. Let's start with binary compounds that are composed of two nonmetals. Look at some of the oxides of nitrogen, and there are several oxides of nitrogen. We've got to name these in an unambiguous way. And what we do is we use prefixes to tell us how many of each type of atom we have. Then we name the atoms and we end it in IDE, ide. And for your purposes, ide is going to mean binary. Look, for example, at N2O. We have two nitrogens, we have one oxygen. So the name of this compound is dinitrogen monoxide. That is very clear. Then look at this one, N2O3. What would you call that? Sure, dinitrogen trioxide. Now, NO, on the other hand, could be called mononitrogen monoxide, but that's getting a little strained. So why don't we just call it nitrogen monoxide? And that will take care of it. There are some common prefixes that you do need to know, and I expect you already do. You know mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. I want you to notice that for 7 we use hepta and not septa. Will you use all of these? Most probably you will. Let's try some. Try this one. Did you get diphosphorus trioxide? Okay. What about this one? When there's only one of the first element, don't use the mono with it. Just call the element by name and use the prefix with that second one. So this one becomes iodine heptafluoride. What about this? Did you say diarsenic pentoxide? Well, you may learn a little different name for it at a later date. What about this one? Oh, yes, you're familiar with that. Carbon monoxide. And what about this one? Tetraphosphorus decoxide. Have you noticed that, for example, with this one, where we have deca oxide, we have an A and an O, two vowels together, that we very often drop one of them. We just call it dec, and we drop the A, and oxide, decoxide. You will find that makes it a lot less strained, if you will. Now let's look at binary acids. What are they? Well, binary acids are solutions of compounds that have hydrogen at the beginning of their formula. And to name it, we use the prefix hydro, and then we name the nonmetal, and we end it in ic acid. Hydro something ic acid. Now understand, we must know that these are aqueous solutions of the compound, or it must be understood. It must be given to us at some way, or it must have AQ written after it, something. Let's look at this one. Here's an example, HCl. Now I put the AQ in parentheses after it so you would know it's an aqueous solution. And this is, what prefix do you use? You use, that's right, hydro. So this is hydrochloric acid, hydrochloric acid. Do you see? What if I didn't have the AQ there? What if you didn't know for sure that it was an acid? What if you had no way of knowing? Then you might very well name it hydrogen chloride. And that would be appropriate because HCl in the gaseous state is certainly hydrogen chloride. But in the aqueous solution, it is hydrochloric acid. Try naming these. How about this one? Okay, hydrobromic acid. How about this? Don't get your tongue hung around your eye teeth now. It's hydroiodic acid. It's not hydroidiotic acid. It's hydroiodic acid. And this one? Keep the faith now. Name it according to the rules. And it is hydrosulfuric acid. This is not the sulfuric acid of battery acid fame. This is hydrosulfuric acid. We'll get to the other soon enough. Well, what about this one? Don't you even think about calling it hydroxyic acid. This is water. And HClAQ, of course you know, is hydrochloric acid. Got the idea? All right, let's go now to binary compounds made of a metal and a nonmetal. Now, the prefixes that we used with the compounds of two nonmetals should be left right there with compounds of two nonmetals. We don't use prefixes with the metal and the nonmetal. What we do is we name the metal, then we name the nonmetal, and we end it in IDE. Why do we end it in IDE? Because it's binary. Here's some examples. How about this one? Oh, yeah, you know this. Sodium chloride, right? Yeah. How about this? Magnesium chloride. Well, how did you know there were two? What about this one? Aluminum oxide. Aluminum oxide. How did you know to use two aluminums and three oxygens? Well, I can tell that you need a table of oxidation numbers. There should be one in your note guide, or you can go out to the site and get one off of our website. Now, here's the table of common oxidation numbers that we're going to be using through this course. Let's consider, for example, let's consider calcium with chlorine, or calcium chloride. If you will look on the oxidation number table, up under the +2, you see that calcium is a +2. Chlorine, what's the charge on chlorine? Go down to the -1 elements and you will see chlorine down there. Chlorine is a -1, calcium is a +2. Compounds must be electrically neutral. Therefore, the formula is CaCl. Binary compounds that contain a multivalent metal. Well, what are multivalent metals? Multivalent metals? Let's look at our oxidation table again. Look here and here. Do you see anything they have in common? Look at the bottom of the +2 column. Do you see that copper and mercury appear in both the +1 and +2 columns? That's because these two elements have more than one oxidation state, and these are the two states they commonly have. You see this repeated again over here. Do you see chromium, iron, manganese, cobalt, nickel, and arsenic in the +3 elements? Look carefully. Yes, there they are. And do you see that all of them except arsenic also appear in the +2? But arsenic also appears as a +5. The lower oxidation state is given an us ending. The higher oxidation state is given an ic ending, as one way that you're going to see used in nomenclature. There are two ways of indicating which ion we're talking about. We can use the old us-ic system that I was just showing you. It is sometimes called the stock system. Or we can use Roman numerals to indicate the magnitude of the charge on the cation. Let's name a few. To name these, you name the metal using a suffix or an ending to designate the oxidation state, the us or the ic. Or you can use Roman numerals, as I will show you. Then you name the nonmetal and you end the compound in IDE, because remember, to you, ide means binary. Here's an example, CuCl. Now you've got to figure out what the oxidation state of copper is. Well, chlorine is a -1, and since these compounds are electrically neutral, copper therefore must be a +1. In the +1 column, if you look at copper, you see that it's the cuprous ion. So this compound then is cuprous chloride or copper 1 chloride. Look at this one. Here we have two chlorines, but again each chlorine is a -1. However, being that there are two of them, the total charge on the chlorine is a -2. So copper must be a +2 for this to be electrically neutral. Generally above the elements, I like to put just the individual charges. If you look in the +2 column, you see this is cupric. So this becomes cupric chloride, or if you will, copper 2 chloride. And you need to know how to do both. Now here's one that's a little different. Look at this. Bromine is a -1, but there are two of them. So it's a total of -2. Mercury then must be a total of +2, but there are two of them. Therefore, each mercury must be a +1. And if you look at mercury in the +1 column, you'll see that it's mercurous. Well, it's written a little strangely, and I'll show you why in a minute. But this is mercurous bromide or mercury 1 bromide. Now, I know it looks strange, but you see the mercurous ion is a dimer, and it actually exists as two mercury ions, +1 ions, bonded together making an overall +2, but for two mercuries. So remember that. It is a dimer. Can you name these? Let's give it a try. You might want to stop the video each time and try your hand at naming each one before I go through it. But let's start here. Here we have a compound of tin and sulfur. I always start on the right-hand side, and sulfur has a 2 negative charge. There are two of them, though, so that gives us a total of 4 negatives. Tin, then, must be 4 positives. There's only one tin, so by itself, then, it has to be a 4 positive. And if you've learned your chart of oxidation numbers, or if you look on it, you will see that tin with 4 positives, or a +4 charge, is the stannic ion. So this is stannic. And it's binary, so it's sulfide. Or, if you will, that is 10, 4 sulfide. Now let's look at this one. Same principle. We're going to start on the right with oxygen, which is 2 negatives. There are 3, which gives us 6 negatives. Iron then must be 6 positives. There are 2 of them, so each one must be 3 positive. That means it is the ferric ion. So that is ferric oxide. The other name is iron 3 oxide. Couple more. Let's try this one. Here's a compound of arsenic and nitrogen. Nitrogen is 3 negative, and there are 5 of them, gives us 15 negative charges. Therefore, arsenic must be 15 positive charges, and there are 3 of those, so each one then must be a 5 positive. That is the arsenic ion. Arsenic. And it is a nitride. Or, if you will, it's arsenic 5 nitride. Remember, "ide" means binary. Now let's look at this one. Here we have chlorine with a 1 negative, and there are 2 of them, so that's 2 negative. So mercury must be 2 positive, and there are 2 of those, so each one must be a 1 positive. And the mercury in the +1 column is then mercurous. So this is mercurous chloride. Or, if you will, it is mercury 1 chloride. Now, did you remember that mercury exists as if it were 2 of them bonded together, Hg bonded to Hg, each one with a +1 charge? It's called a dimer. And that is why it exists this way. Mercury is not the only dimer, but we'll see others later. Here we have several different compounds to name. Let's see if we can remember how to do all of this without going back and looking up the directions. Now, starting with this first one right here, we have a compound that starts with hydrogen. It's binary, and it's aqueous. Therefore, it's an acid. So we know that it is an acid. Now, if it's a binary acid, its prefix is hydro. So it's hydro, and then the acid is sulfuric acid. Hydrosulfuric acid, not to be confused with sulfuric acid. This next one now, let's look at it. Here we have a binary compound of a metal and a nonmetal. The metal, does that look familiar to you as possibly a multivalent metal? Sure. Oxygen is 2 negative. There are 3 of them, which gives you 6 negative. Therefore, manganese must be 6 positive, and there are 2 of them. Therefore, each manganese must be a 3 positive. And have you learned them? Do you recall that manganese with a +3 charge is manganic? Manganic oxide, or, if you will, manganese (3) oxide. All right, let's look at this next one. This is binary, but it's 2 nonmetals. And with 2 nonmetals, remember, we use prefixes. So this is tetra phosphorus decoxide. Remember, when we have the A and the O together, we're going to drop the A and keep the O. And so that is why it's going to be the decoxide. So we will erase this and put in the name that we need here. There's my pointer. I know it's around here somewhere. There it is. Oxide. Tetraphosphorus decoxide. All right, let's go down to this next one. This next one is a metal and a nonmetal. Chlorine is a -1, giving us two negatives. Mercury then must be a +2, two positives, and there's only one, so it must be two positives. And being two positives and only one mercury, it is the mercuric chloride. Or, if you will, you could refer to it as mercury 2 chloride. Now, let's go on to the next phase of nomenclature. Now we're ready for ternary nomenclature. Nomenclature of compounds made from 3 different atoms. We're going to do 2 types. We're going to do acids, and then we're going to talk about naming compounds that contain a metal and a polyatomic ion, which, as you know, I very often call radicals. Let's start with these ternary acids. Now, how do we recognize them? Well, acids have hydrogen at the beginning of their formulas, the most common way that you recognize them. So it's H sub M, X, O sub N. When we talk about ternary compounds or ternary acids, they're going to have hydrogen in them, they're going to have oxygen as a rule, and they're going to have something else in the middle. There is an exception, but we'll deal with that later. They consist, if you will, of hydrogen and a polyatomic ion now, or a radical. Let's go back and have a look at the oxidation numbers again. So pull out your oxidation sheet. Now, if you look at this, I'm talking about the radicals or polyatomic ions. These are the ones I'm looking at. Yes, there's a batch of them up under, or a couple of them up under the +1 column, but we're not talking about these. We're talking about the negative ones down here in the bottom. That is a lot of different polyatomic ions. And remember, put them on flashcards. It's the easiest way to learn them. Now, keep a copy of this oxidation number sheet in front of you as we go through the nomenclature. To name these acids, what we do is we consider the radical or the polyatomic ion first. Now I'm giving you H3BO3 as an example. Identify the radical. Here's the radical. When you look on your sheet, what is the radical? Well, you say, well, what do I look under? -1, -2, or -3? Hey, the easiest thing to do is look at the number of hydrogens. There are 3 hydrogens in this, and each hydrogen is going to be a +1. Therefore, that radical over there has got to be a -3. See? So that, you see, then, is the borate radical. It's the borate radical. Okay, now, to name the acid, you do it this way. You name the radical. But you don't use the radical's ending, you change it. I'm going to give you the radical endings and the acid endings. If the radical ends in ate, A-T-E, the acid is an ic acid. Ate for the radical, ic for the acid. You feel icky from something you ate. I don't care how you remember it, just remember it. Ite is going to give you an us acid. So if the radical ends in ite, the acid will end in an us acid. Okay, let's look back up at this acid we have. What's the radical? That's right, it's borate. So if the radical ends in ate, the acid ends in ic acid. So this is boric acid. Do not use hydro. Hydro means binary acid. Got it? Good. Let's go on. Try these. Here's this one. What's the charge on the radical? Yep, -1. So look at it, and what's it going to be? I get nitric acid. How about this one? What's the charge on the radical? Look it up. What's the radical? Do you see it? It's the carbonate. If it's the carbonate, then this is carbonic or carbonic acid. Carbonic acid. There's some question as to whether or not that exists like that, but that's okay. We can still name it. Here's one. Oh, look. There's one hydrogen, so that radical is a -1. So look under there, and do you see that this is the perchlorate radical? So this acid then is perchloric acid. Dangerous acid. We don't like for you to handle that much. Here's another one. What's the charge on the radical? That's right. And what's the radical? Yeah, it's the phosphite radical. Therefore, this is, now you're going to have to add an extra syllable for ease of pronunciation. And this becomes phosphorus acid. Phosphorus acid. What about this one? There are all kinds of silly poems made up about this one. Okay, it's the sulfate radical, so it's sulfuric acid. Poor old Johnny, gone forevermore, for what he thought was H2O was H2SO4. You're going to hear all chemists are terrible about this. Look at this one. What about HNO2? And that's the nitrite radical, so this becomes nitrous acid. Are you getting the idea? Here we have a series of acids. Let's see if we can try our hand at naming them. Now, this first one that we look at is a ternary acid. And as a ternary acid, the first thing we have to do is figure out what this radical is. Well, BrO4 with a -1 is the perbromic, or the perbromate, the perbromate radical. Well, the perbromate radical then is going to produce perbromic acid. Down here at this next one, again, it's a ternary acid. It has this radical, which is the, what is it? It's the oxalate radical. Therefore, this is oxalic acid. Now looking at this next one, oops, it's a binary. And binary then, remember, prefix is hydro. Then you name the nonmetal and end in ic acid. So it's hydrochloric acid. This next one is very similar, but it's ternary instead of binary. And this radical is the hypochlorite radical. And as the hypochlorite radical, it's going to give us hypochlorous acid. Hypochlorous acid. An excellent bleach, by the way. Now down in this last one, we have a radical right here. This is a ternary acid, and that is the phosphate radical, and therefore this is phosphoric acid. Phosphoric acid. Good. Got the idea? This is a good stopping point for this lecture. But I tell you what, when we come back in the next lecture, we'll start out with naming salts of ternary acids, and we'll wrap up this unit on nomenclature. A better way to teach and learn chemistry.